Hello everyone, I am Dr. Kiranmayi, Area Chair and Assistant Professor, Digital Transformation and Operations, School of Business, Aditya University. In this present lecture, I am going to discuss a special case in transportation problem, that is nothing but degeneracy. So, how to find out degeneracy and what is the meaning of degeneracy, how to resolve this degeneracy is going to be the point of discussion of this present lecture. Degeneracy means where the solution gets repeated or another solution may exist for the same transportation problem. So, how to find out degeneracy? So, we have three methods to find out initial basic feasible solution, that is VAM technique, northwest corner method, least cost method. So, using any of these three methods, we find the initial basic feasible solution, right? So, after finding this initial basic feasible solution, using this formula m plus n minus 1, m represents number of rows, n represents number of columns. So, if m plus n minus 1 is equal to number of allocations, then the solution is non-degenerate. If m plus n minus 1 is not equal to number of allocations, then the solution is said to be degenerate or it is a case of degeneracy, we can say, right? And this degeneracy may occur at two stages. One is initially when we find initial basic feasible solution, at the level of initial basic feasible solution only degeneracy may occur, or degeneracy may also occur in the subsequent iterations during optimality test to find out, to move on to the optimum solution, right? So, here is one problem, right? Here we are given a problem, we are having 3 sources and 5 destinations, right? And so, in the beginning, in the previous lecture, I have told you that first we have to, whenever we are solving the transportation problem, first we have to look at the problem whether it is balanced transportation problem or unbalanced transportation problem. So, total demand in this problem is 25 and total supply is 22, right? So, but therefore, total demand is not equal to total supply, it is unbalanced transportation problem. Therefore, we have to make this unbalanced problem into balanced one, then only we can solve the transportation problem. Here, total demand is greater than total supply, therefore, add one total supply as one dummy row with 0 unit cost, and the difference, that is 25 and 22, the difference is 3 with 3 units of supply. So, this is how we can transform the unbalanced transportation problem to balanced transportation problem, right? And after doing this, the next step is to find out IBFS. So, it is here we have a solution which is called IBFS, which is obtained using VAM technique, Ogle's approximation method. This is the initial basic feasible solution which was obtained. And now, how many now we have to, before proceeding for optimality test, we have to check whether it is having degeneracy or not. To check whether there is existence of degeneracy, okay, first we have to compute m plus n minus 1. So, m means number of rows. How many rows we have? 1, 2, 3, 4 rows we have, plus how many columns? 1, 2, 3, 4, 5 columns are there, minus 1, that is 9 minus 1, 8. So, we should have 8 allocations. Let us count how many allocations are there. 1, 2, 3, 4, 5, 6, 7. 7 allocations. So, 8. Here m plus n minus 1 is not equal to number of allocations. Therefore, it is a case of degeneracy. There exists degeneracy in the problem. So, the next thing, how can we remove this degeneracy? To resolve degeneracy, we add an artificial quantity, a small quantity which is called D, and to which cell this small d must be added. For unoccupied cell which is having minimum transportation cost, for that unoccupied cell we have to allocate this d value so as to obtain 8 allocations, right, in order to resolve degeneracy. So, in this problem, among all the unoccupied cells, it is 5, 8, 6, 6, 7, 7, 5, 8, 4, 4. Okay, so 4 is very small among all. Therefore, to this cell, this d value is given, is assigned. Therefore, for this cell, that is 3, 5, cell 3, 5 is given allocation D. Now, number of allocations 1, 2, 3, 4, 5, 6, 7, 8. Therefore, m plus n minus 1 now is equal to 8 allocations. Now, we can proceed as it is how we have found optimum solution using Modi method. The same procedure we have to follow to find out the optimum solution, and we can check whether the IBFS is optimum or not. If it is not optimum, we can compute UI Vj values, and then we can compute Dij values for unoccupied cells and look at Dij values whether all are positive or not. If it is not positive, proceed for the next iteration. If all the Dijs are positive, then the solution at that stage is going to be the optimum solution. Okay. So, this is how we can resolve degeneracy if it exists in the first stage itself, at the stage of IBFS, right. But this degeneracy may also occur in subsequent iterations, right. Therefore, when degeneracy occurs in subsequent iterations, look at the cells which have become unoccupied very recently, okay, that is in the previous stage. So, check the cells which have become unoccupied very recently and the cells which are having, the unoccupied cells which are having least transportation cost. For those cells, you can allocate a small value called epsilon, or D you can also say, D or epsilon, which is a small quantity. We have to allocate the those unoccupied cells which have become unoccupied very recently, which are having less transportation cost, minimum transportation cost among all the other. And this is how we can resolve degeneracy if it occurs at subsequent iterations. And then we can proceed as it is using Modi method to find out optimum solution. Therefore, by the end of this lecture, we have understood how to identify degeneracy, what is the meaning of degeneracy, and when degeneracy occurs, and how to resolve this degeneracy when it occurs at the stage of IBFS and if it occurs at subsequent stages. We have understood by the end of this lecture. Thank you.